Hello aviators, I welcome you on board flight of Captain Vijay in the series of flights to study radio aids for Dgca CPL and Atpl examination. Today we will fly through the topic ionization layer and sky waves. In this video lesson, we will learn what is ionization layer in the atmosphere and how it helps in generating sky waves. So fasten your seat belts as we are ready for takeoff. To understand this topic better, we need to understand two things beforehand. First is ionization and the second is total internal reflection, and let us understand them one by one. Ionization. All atoms are electrically neutral. This happens since number of negatively charged electrons going around the nucleus in different orbits are same as number of positively charged protons held in nucleus. So they are electrically neutral. But when electrons of an atom is excited by impact of energy, electrons leave the orbit and becomes a free electron. And the atom with one electron less is called positively charged ion. They can recombine later to become neutral again. So the process of exciting electrons to release them from the mother atom is called ionization. Total internal reflection. We studied in previous video that when a wave travels from one medium to another with a different refractive index, it changes its speed and direction. So if you point a torch from the bottom surface of a swimming pool towards water surface, as it leaves water and travels in air, it will accelerate and turn away from normal. This is called refraction. But if we keep increasing the incident angle, there comes a point when the light will get reflected back in the water and will not travel outside the pool. This phenomena is called total internal reflection. And the incident angle at which this starts to happen is called critical angle. Ionosphere. There is a layer in upper atmosphere called ionosphere, starting at 60 km height and extending up to 1500 km. In this region, incoming solar radiation interacts with the atoms, raising their energy levels and causing electrons to be ejected from the atoms. The result is negatively charged electrons and positively charged ions. Since ionization is caused due to solar radiation, highest intensity of ionization will be found shortly after midday, about 1400 hours, and the lowest will be just before sunrise. In summer, the ionization will be more as compared to winter, and ionization will be more at lower latitudes since the intensity of solar radiation is more near equator. As the incoming solar energy is absorbed by the gaseous atoms, the amount of energy available to ionize the atoms at lower level reduces. Hence, ionization is more at higher altitude. Now let us discuss about ionization layers. There are a total of 3 prominent layers of ionization in atmosphere, and they are called D, E and F layers. D layer is the lowest and occurs at an average altitude of 75 km. This layer forms at sunrise and disappears at sunset. So this layer is present only during the day. The next layer is E layer at an average altitude of 125 km. It is present throughout 24 hours. After sunrise, E layer comes down and again goes up after sunset. The final and highest layer is F layer at an average altitude of 225 km. The F layer splits into two at sunrise, and they are called F1 and F2 layers. And F1 and F2 layer rejoins at sunset and again becomes F layer. In general, ionization increases from sunrise to midday local time and then decreases until next day sunrise. The structure of ionization layer gives stable conditions by day and by night. However, around dawn and dusk, the ionization layers are in transitional state. So radio navigation and communication systems using the ionosphere are subject to excessive interference and disruption during dawn and dusk. The ionization intensity within a layer is maximum in the center and reduces towards the top and bottom boundaries. Refractive index of ionization layer is less than 1 and that of atmosphere is slightly more than 1. So radio waves traveling through this layer would undergo refraction. Waves would accelerate and then turn away from normal since they are traveling towards a medium of lower refractive index. Similar to the scenario we discussed for the swimming pool. At critical angle and beyond, the radio waves will undergo total internal reflection and will be reflected back towards the Earth's surface, and these waves are called sky waves. Now let's discuss some terms and definitions associated with sky waves. Starting from the vertical at the transmitter, as the angle between the vertical and the radio wave increases, an angle will be reached where total internal reflection occurs for the first time and the wave returns to the surface of the Earth. This is known as first sky wave return, and the angle at which this occurs is called critical angle. The distance from the transmitter to the point where the first sky wave return appears at surface is known as the skip distance. Sky waves occur in the LF, MF and HF frequency bands. In these bands, radio waves also travel along the surface of the Earth called surface waves. From the point where the surface wave is totally attenuated to the point where the first sky wave return appears, there will be no detectable signal, and this area is called dead space. Remember, VHF and above do not produce sky waves. And the amount of refraction experienced by the radio waves is dependent on both the frequency as well as intensity of ionization. So let us discuss the effect of frequency and intensity of ionization one by one. First, let's see what is the effect of change of frequency. For a given ionization intensity, higher the frequency, lower will be the refraction. So as the frequency increases, higher critical angle will be required for reflection, and consequently the skip distance and dead space will also increase. As frequency increases, the surface wave range will decrease. So there will be an increase in dead space caused by both the increase in skip distance and decrease in surface wave range. Effect of intensity of ionization. At a given frequency, higher intensity of ionization further reduces the refractive index and radio wave direction would change further away from normal. This means that total internal reflection will take place at a smaller critical angle and the skip distance and dead space will decrease. Height of the layer. The skip distance will also be affected by the altitude of the refracting layers. As the altitude of the layer increases, the skip distance will also increase and greater ranges will be experienced by reflection from F layer as compared to E layer. Ranges of sky waves. Average maximum range achieved from the E layer is 1350 nautical mile and average maximum range from F layer is 2200 nautical mile. Multi-hop refraction. This is a scenario when a radio wave is reflected back from ionosphere, then this sky wave is reflected back from the Earth surface again towards ionosphere for a second reflection, and this cycle goes on. This is called multi-hop refraction, and multi-hop sky wave can achieve ranges of as much as half the diameter of the Earth. HF transmission. For short range aeronautical communication, VHF line of sight frequencies are used. To get long range coverage over land, we can keep installing VHF transmitter at every 200 miles. But how do we get long ranges over oceans where we cannot install VHF antenna on sea surface? So the only practical means of communication over long ranges over oceanic area is skywave. And HF is widely used for long range aeronautical communication, especially over oceanic regions using skywave. Since ionization intensity is lower by night than by day, it means that the frequency required for use at a particular range by night will be less than that required by day. So HF frequency required for communication at night is roughly half that required by day. Important from exam point of view. Because skip distance increases as frequency increases, low frequency will give short range and high frequency will give longer ranges. Now let us discuss a phenomena of super refraction in VHF. VHF and above follow line of sight and ranges are limited to radio horizon irrespective of transmission power, but depending on atmospheric conditions and refractive index of prevalent atmospheric layers, they get refracted towards the surface of Earth and slightly longer than line of sight range is achieved. Super refraction, as the name suggests, is higher degree of refraction. This can occur in VHF transmission. Radio waves experience greater refraction, that is, they are bent towards the Earth's surface more than what is there in normal conditions and giving notable increase in line of sight range to as much as 40% more than the usual range. The conditions which give rise to super refraction are decrease in relative humidity with height, temperature lapse rate less than standard, high pressure systems, warm air flowing over cool surface. All these conditions just lead to one thing. They are reducing the refractive index with increase in height, so radio waves keep getting refracted, curves towards the Earth's surface and give larger ranges. Duct propagation in VHF. Duct propagation in VHF is similar to or akin to multi-hop refraction of HF in sky waves. VHF signal sometimes can get trapped in an atmospheric duct and keep getting internally reflected multiple times, and it can achieve extremely long ranges. So hope this video has made you understand ionization layer, sky waves, critical angle, skip distance, dead space and HF transmission. With this we have arrived at our destination. Subscribe the channel for more such informative videos on aviation. Like, share, subscribe if you wish. Comment on the section below if you have any query or question. Hope to see you on board again for the next flight. Until then, happy landings.